Greetings. All right, let's get a screen here. Wake up machine, come on. Must be Thursday. Kale's here. That's good. That answers one of my questions. I got up this morning and was like, is it Wednesday or Thursday? I have no idea. Yes. Well, we have a very few applications left, and we're going to look at one today called linear approximation, which is well named. And by the time we get done, you'll say that's a perfect name. But before we get into linear approximation, how about other things that are on your mind regarding maybe the assignment or the homework that you're working on this week or the project that we did yesterday? Anything you want to weigh in on at this early hour?
I have been struggling to get through 4.5. I got like the first problem done, and all of the others, I cannot do them.
Yeah, since you ask, let's just take a quick second and look at that. Yeah, optimization is a challenge, and so just random thoughts. Let's see. I don't remember if I did a Norman window. I think I did a Norman window example in your class. I don't think I did one in the other one. Um, Ask me questions now, April, since you're in here, because I think this is a challenging enough that other people might benefit too.
So I was trying to follow along with the videos and do the same steps they were doing, and I still was not able to get them right. And I don't know why, and I had that problem with multiple
Mm-hmm.
questions. And I don't know if that's because I keep doing the same thing wrong or not.
That could be. I mean, I'd like to look in detail at what you actually tried. Um, there's little things. I mean, I have had to fix some of these questions. This question number 3 was actually broken, but we got it fixed. I don't know, a couple of days ago, I think. So it could actually be that you were getting one of them right, and it didn't think you were. Little things like this question, you're looking for the rectangle, and because this particular graph has no x term, that means the parabola is centered on the y-axis. It's symmetrical on the y-axis. And so the rectangle itself is going to go x to the right and x to the left. And so the actual width will be double the x value over on the right hand side. It'll be double since there's an x to the left and an x to the right. So there's like some little things that you could do wrong.
Oh, that's why I got that one wrong.
So
Okay, thank you.
So yeah, my guess is it's little things, but I really would like to talk with y'all, even one on one. But we should have some time after class where we could actually, maybe before class is even over today. It's not a very long explanation today. Um, because it's really nice to have somebody look at your work. I mean, it's nice to watch a video. It's nice that a lot of these questions have videos that go with them, but it's even better if somebody can look at your work and help you correct your own thinking, which is kind of an individual sort of thing.
Yeah, I don't know about those videos, but I know sometimes the videos are just like they're like a similar example, but they're not like exactly the same, you know. Like,
Yeah. Which is, from my perspective as a teacher, kind of good, because you do want help on things, but you also don't want to just copy somebody else doing it. I mean, if you're utterly lost, I think that's a good place to start. Don't get me wrong, because you do have to, reverse engineer things a lot of times. Because as I said, this section's hard because although I think I got to 6 examples in the 2 days I taught this, Monday and Tuesday, it's almost not helpful because every question's different. So
yeah, I mean, it makes sense. It's teaching us to think for ourselves.
yeah, but you need some guidance on that. I mean, I can't just do 6 examples and then you do a totally different problem and then so you just get it. Like that's unlikely to happen, I guess is what I'm saying. So hit me up like this weekend, for instance. I'm going to be around drawing house plans and stuff a lot. So we could do a little one-on-one Zoom a whole bunch of times over the course of the next few days with respect specifically to 4.5, because it is one of the things I'd love you to leave being able to do, just because it does demand a lot of creativity and teach you a lot of algebra and so forth. But a lot of times it's like literally a 1-minute nudge where we have a little conversation. You're like, oh, okay, I'll try that. And then zing, you're gone and off you go. So please don't feel like you're imposing on me to do that. So I might see an email and it's a good idea to message inside my open math, this message instructor business, just because I can actually open it up and see the exact question you had. And so that's pretty helpful too sometimes. So you might take advantage of that.
We'll say it's probably better than what my electronics class is right now. I'm doing a bunch of labs that were written for a completely different hardware device, and like I got to figure out how do they work on this other device. Because they haven't rewritten the labs yet, you know. But it's like at this point in my education, I should probably be able to figure that out.
That does not sound enjoyable.
I mean, it's not bad. I'm going for electronics, so I should enjoy things like that, you know.
Yeah, learning's painful. I know in my own case, I mean, up to this very day at my age, when I'm learning something new, it still feels like impossible, or something's weird. I'm just not getting it. And then when I get it, I look back and I think, how did I not get that? It's so clear now. But that's why I'm always kind of talking about soak time and think time, your ability to. There's no substitute for that. I mean, to sit and soak on a problem, meaning basically you're not making any progress, but you're thinking about it. Like, it's an odd thing, but I think that's important, far more important than watching a video where somebody does it for you, or listening to me just do it for you. Anywho. All right, this is kind of cool. Again, what we're really doing in chapter 4 is looking at applications of derivatives, and there's really a couple of them that are kind of neat. And this one isn't super relevant or something you're going to use a bunch, but it's actually connected to something that we're going to talk about later on that I want to quickly mention. So for instance, you have in Math 111, you were able to find the zeros of a function, which is that point right there. Then you had this cool little trick where you could just go in there and say, I'm looking for a 0, and what's my lower bound and what's my upper bound, and then what's your guess, and you put your guess somewhere in the middle, and it just goes bang and just highlights in on that and gives you the answer like to 6 decimal places. And so we're accustomed to thinking that machines are magic in our generation. It's like, oh well, yeah, it's a machine, of course it can do it, but it's based on calculus that it can do it. And it actually is honing in on it. It's actually getting it by successively approximating it just really quickly. And calculus makes that approximation process really fast. And so today's topic, although it isn't that, is kind of based on that. But I'll just illustrate the beauty and simplicity of the principle. If you were to make your guess, say right here, And by the way, this is the reason your calculator asks for a guess. Although incidentally, Desmos does not. Desmos kind of hints or seems to understand you might want to find where an x-axis, where it crosses an x-axis, an x-intercept. And that point right there that you're after is already kind of grayed in, and all you got to do is hit it and it just goes boom, there it is. But in your graphing calculator, you got to give it a guess. And so this is kind of what's happening actually, is if you give it a guess, what it's doing is finding the equation of a line through your guess. And you notice by extension, that line actually hits really close to the right answer right there. So the concept of like, how do I improve my guess? You improve your guess by using calculus to find the slope of the curve at the point at which you guessed it. And then you get sent over to the place you're interested in. You're really close. I mean, does that concept make sense? So what are we doing today? Well, notice that is a line, and we're using the line to approximate something, and that's exactly what we're going to talk about now. So let me do a specific example. So let's say that we wanted to approximate the square root of, say, 104. Now you already have an answer to that in your mind, and I'd like you to take a guess at it, like an actual genuine educated guess, like guess it accurate to 2 decimal places. I mean, and I definitely mean guess at that. Now what you should
10.0.
Go ahead.
10.032, something like that.
Yeah. So
well, no,
we're glitching. You should definitely see that it's 10 plus, right? A hair over 10. And you certainly would say it's not like 10.4, right? Because the square root of 100 is 10. And so this is just over that. And so beyond that, you should just be guessing. So I'm saying guess to 2 decimal places, or maybe 1, you know? So is it 10.1? That certainly sounds reasonable. Is it a little below that, like 10.08, or is it a little above that, like 10.12? Again, I don't really know, but I know I'm guessing in the low 10s. Do you agree with that? I mean, that's what you're guessing too, right? Well, keep in mind, again, this is sort of idiotic because, you know, we, in our culture, because, you know, we have this machine and there's no reason to guess. We just bust it out and it produces the answer. But it turns out that a square root is not that simple. I don't know if you've, actually, I'll give you extra credit for this because I think I know the answer to this, but I'm actually not sure. But, you know, what is it that's inside your calculator that finds the square root? In other words, you are here looking for a number that when squared is 104, right? And since the answer to that is an irrational number, meaning a decimal that goes on forever with no pattern, no repeats, how does the calculator even produce that? You know, is there some magic function that we don't know about? And the reality is the calculator does not know. It's actually a computer programming. This is at least what I think I understand. It's a computer programming concept where, in a sense, if you said, I'm going to just speak extemporaneously and kind of know what I'm talking about here, but not really. And so let's say you said it was 10.1. And so then you take 104 divided by 10.1. Does it make sense if the answer is 10.1, then you got it correct? Hey, you nailed it. But what if it came out, say, 10.2? Does it make sense that you know the answer is between 10.1 and 10.2? And so the idea is then, could you kind of maybe take the average of those two and say, oh, it's 10.15. And then you sort of start over and say, okay, 104 divided by 10.15. Again, if you get 10.15, that means you got it right. But what if you get 10.19? Well, now you know it's halfway between 10.15 and 10.19. So you'd guess 10.17. Does it make sense? Computers are really good at stuff like that, I mean, I think that's the gist. I think it's
Yeah, basically that makes sense.
but that's the gist of what your calculator is doing. It's just good at it. You and I are terrible at that. And even that division that we have to do right there is kind of time consuming. So just out of curiosity, because I don't know, I just like to think, I'm actually going to try this. And again, it feels weird to grab your calculator and do this, because why? If I grab your calculator, why not just take the square root of 104? But I'm going to take 104 divided by 10.1, and I got 10.297. So if I average, if I average those two, I get about 10.199.
You are right about the programming thing. We had to do something similar in C++, where we had to like create a few different programs that did basic calculator functions, and then like one that did like Pascal's triangle.
Yeah.
And it was interesting, like, because it shows how complicated of an algorithm you have to put in there to make some simple math function happen.
That is so true. And that's really kind of neat to see that, because, most of us just take this machine for granted, but, we're standing on the backs of giants. I mean, it's math, it's calculus sometimes that's produced all of this.
Yeah, because it really only understands like multiplication, division, addition, and subtraction. Other than that, everything else is programmed as algorithms into it.
Would you agree that since I got 10.199 for the average of the previous answer, and then when I divided, I got 10.197, that 10.198 is darn close now? So that's kind of the process that a calculator goes through. But that's not very sophisticated, because you're taking an average and so forth. And a lot of what makes computers difficult is trying to figure out how to reduce the number of times it has to follow an iterative process. Like I sort of got, because I just made an educated guess. And remember, computers can't do this. Computers are not good at estimating. Like they don't know a good estimate for that is 10.1. Like where are they supposed to start? It probably, a computer would start at half, like 5. The first guess would be 5 or something sort of inane like that. I'm not sure how it would do it. Maybe it would round that number off, and I'm not sure what it would do. But if you started with your guess at something more mechanical, like just take the number and cut it in half, so your average, so the half of 104 is 52. So then you start with 52, so it's 104 divided by 52. You can appreciate this would take a lot longer. So I started with an educated guess, and it only took 2 steps, but computers can't do that. So calculus sometimes allows you a way to, speed that process up, and computer programmers are always looking for ways to get the answer they need in like 3 iterations or 4 or 6, but not thousands, because that takes a lot of computer processing time. And so people will come up with brilliant ways to speed that process up. And that's kind of what I want to get at here. So I guess it's important that you understand that this was an educated guess, highlighting the word educated. All right. So you and I know it's around 10.1, but it turns out, no, it's actually more like 10.2. And by the way, that really surprised me. I thought it was going to be under 10.1. I was guessing like 10.08. I thought it was going to be a lot closer to 10 than 10.2. So that kind of surprised me. So here's the idea. Here's the process using calculus to get an estimate of this. And you can appreciate people in the pre-calculator world, which was most of history, would have been more impressed with this than you and I are. So I'm really interested more in it as a thinking device than I am like, let's go use this, because we have computers that do all this stuff. So let's consider then, well, we're taking the square root of a number. And so let's consider the equation, the square root of, well, a number, square root of x. And so you roughly know what the square root of x looks like. get it on Desmos or on your calculator if you want, but that's what a square root graph kind of looks like. And so the idea is this: we're out here at 104 and we're trying to find, if you will, that y coordinate right there, right? Because if you stick x as 104 in, then the y coordinate is your answer to this. So we're trying to find that y coordinate up there. And we can't, because the square root of 104 is not a perfect answer. But what if we did this? This is the idea here. What if we backed off? And I'm going to blow this up a lot. I'm going to back off. Let's say we backed off to 100, and notice it would be way closer to, that point would be way closer to 104 than I just drew it. But if we backed off to 100, and we found the equation of that tangent line right there, does it make sense we could use that tangent line to sort of boost forward from 100 to 104, and we'd have a really close estimate? Now that estimate would get us to this point up here. And so does it make sense, our estimate based on the graph I just drew, does it make sense this estimate's going to be a little big? Not only is an estimate, we actually know it's a hair large. So how would that work? Well, what is the equation of that tangent line? We're really good at lines. We have no problem with those. And again, I'm not teaching you anything you can't do right now. You just haven't thought of this idea before. Well, I know what the derivative is. And why am I taking the derivative?
So you can be able to find an equation for that tangent line, because you need to know the slope.
Yep, couldn't be said better than that. I'm looking for the equation of a tangent line, and don't I have to know the slope of the line? And that's what derivatives tell us is the slope. And so if I take its derivative, notice this still involves a square root. So it's not like I can stick 104 into that, because it's not like I can make the line, I can't have the line hit the curve where x is 104, because I don't know what the square root of 104 is. That was the whole problem in the first place. But I do know what the square root of 100 is. And that's why I picked 100 a minute ago, by the way. That's the sort of the closest point I can find that I know the answer to the square root of. I know the square root of 100. And so if I figure out what's f prime of 100, 1 over 2 times the square root of 100, that's 1 over 2 times 10, or 1 over 20, or 0.05, however I want to manage that. Then I know this much of my tangent line. I know it's 1/20th x. How am I going to get the y-intercept? Well, related to that same exact point, don't I also know, along with x is 100, don't I also know what the y coordinate of that point is?
Yeah, I mean, if you plug it into the original equation, you should.
Yeah, if I plug it into the original equation, that's again why I picked 100, then the square root of 100 is 10. And so that's the point, x is 100, y is 10. And so I have a point and I have a slope. So if I know that y needs to be 10 when x is 100, then I can say 10 equals 100 divided by 20 is 5. Then that means this is plus 5.
I have a question. With the 104, I mean, I'm assuming it's just a special thing with this number, but couldn't you also just take the square root of 100 times the square root of 4?
No, because 104 is 100 plus 4, not 100 times 4. So you could say it's the square root of 100, the square root of 100 plus the square root of 4,
Oh,
but then you'd be screwing up the order of operations.
yeah, I wasn't thinking of that properly.
That's a great thought. I love it. Chime in immediately. So Would you agree that this is the equation of the tangent line? But what good does that do me? Like, good for you. You found the equation of the tangent line nearby. What good does that do you?
I mean, it would give you a point that's really close to what you're looking for, correct?
Well, look at this graph over here. I mean, when you zoom in, isn't the green line and the blue curve almost look identical to each other? And maybe in a minute I'll graph it in Desmos, or a next problem I'll graph it in Desmos so it isn't all terrible looking like mine. But the point is if as long as I'm fairly close to the point 10, 100, they're kind of indistinguishable, aren't they? Like the line and the curve almost look the same. Now, the further I go away, by the time I'm over here, it's starting to separate from the curve, but it hasn't separated very much. And so because it hasn't separated very much, does it make sense that I could go back and say, okay, cool. I don't know what the square root of 104 is, but if I switch to the line and stick 104 into it, do you see what's happening here? I'm going to get that, well, that red point. I'm going to get that red point up there, which is just a hair above the actual point that I'm interested in. And notice the math of that is, oh, all you have to do is take 1/20th times 104 and add 5 to it. Notice I don't need a calculator now. Like, I'm getting the answer to a square root question, and all I have to do is multiply and divide, which again, all people in history could at least do by hand, even without calculators. Remember, they can't even do fractions or decimals without doing it by hand. And so this is, again, much more exciting to, the caveman learning math than it is to you and me. Doesn't this feel like a total waste of time? Like, I got a calculator button for this. But remember, your calculator is not getting the answer because it somehow has a magic function in it. It's getting it because of the iterative process I just showed you. So let's see, what is 104 divided by 20 would be 52 divided by 10. That's nice, because that'd be 5.2. 5.2 plus 5 is 10.2. Isn't that amazing how accurate that is? No guessing and checking. And so it's not impossible that that's what's programmed into your graphing calculator. In other words, when I went back here and I said, what's a calculator going to do to make it a guess at the square root of 104 when it doesn't have the ability to make educated guesses like you and me? Wouldn't this process allow it to start with a guess of 10.2, which is actually almost the correct answer? Well, maybe you say, if we again used our brain to choose the point X is 100 because that was nearby and we know the square root of 100. So we can say then, hence, without a calculator, that the square root of 104 is pretty close to 10.2. And given that the calculator says, I'm cheating now, the calculator says the answer to this is square root of 104 is 10.198, of course, which is what we just saw a minute ago by our own little guessing iterative process. But I'll go ahead and write a few more numbers here. 3903. Again, you need to understand that that's not the exact answer to this. That's what my calculator shows, but the answer is ... goes on forever, no pattern. Nobody actually knows what the square root of 104 is. Have you ever thought about that? That's why we write it as the square root of 104. And basically what we're saying is, well, I don't know what the number is, but it's a number that when squared is 104. And it's around 10.2. And so for practical purposes, around 10.2 is good enough for all of us. So you're used to thinking, yeah, I know what the square root of 104 is. It's approximately 10.2. But it should kind of blow your mind that nobody actually knows what the square root of 104 is. Isn't that weird to think about? No one's ever seen it. And by the way, there are nerds in contests with math. Do you know that? Like, there's contests going to this day to who can calculate pi to the most decimal places accurately, because that's a really interesting irrational number because it pertains to circles and all kinds of crazy stuff that I'll show you during this next few terms. But nobody cares about the square root of 104, right? So no one's in a contest to see who can get the square root of 104 the most accurate. But pi, there's a race, and it's huge, the number of decimal places. And of course, there's people trying to memorize it to the most decimal places and so forth. But you can't write down the square root of 104 without saying approximately. It's impossible. So that's kind of a nifty trick. That's kind of what it comes down to. You can approximate. You can approximate it. Well, what did I say this was called? Linear approximation. You can approximate an answer by making a line tangent to the curve nearby. Now, as a memorized process, for some reason, I remember learning this, and it was like I was always plugging the wrong number in at the wrong time. Like, for instance, you know, down here, I wanted to plug 104 in there instead of 100. Like, you really have to have a clear picture of what you're doing here. You have to have a clear picture that I'm picking a point that I do know something about that's not the point that I want to know something about. So again, the other thing that's really cool is based on this graph, remember what I said, that based on the graph, the green line is above the blue curve, and therefore my estimate of 10.2 is not just a good estimate, I even know it's an overestimate. Isn't that cool? And how much did we miss it by? We missed it by 2 1,000ths. I mean, that is really accurate. So not only did we know it was under 10.2, but it was only off by 2 1,000ths. And so that's the separation between these 2 points. The distance between the red point and the blue point, 2 100,000ths. You wouldn't even really be able to see that on a graph. Now, why did that work so good? Well, because 104 is pretty close to 100. Does that make sense? I mean, if I'd have chose something that was a lot further from 104, like 90 or something like that, or I'm sorry, from 10, if I was asking what's the square root of 112 or something, it would have been less accurate. Also, this curve is real flattish. In other words, it isn't sweeping and making a sharp turn right there. It's a fairly flat curve. The second derivative is actually not very big because the slope is not changing very much right there. So this is best case scenario. But if you will, isn't that kind of cool if you imagine being a caveman and not having a calculator to figure out the square root of something? I mean, isn't it cool that you can, if you needed for some reason the square root of 104, that by just basic math processes and no calculator, just decimals and fractions, like stuff that you can do by hand without a calculator, you can come up with an estimate for a square root that good. And isn't that even better than this method here? Because if you guess 10.1, 104 divided by 10.1 is a long division problem. Can you still do long division? And then when you get 10.297, then you've got to add 10.297 and 10.1, add them by hand, divide by 2. And now you get a really accurate answer, 10.199. Now you got to divide 104 divided by 10.199, get an answer. Like you got to do that all based on long division. And so this is really a slick idea when you look at it historically. Again, utterly irrelevant to us, but it's a pretty stinking good idea. So I just think it's a neat factor. This is one of the things. This is a section I would skip if we didn't have time. But I think it's kind of just neat to see what people thought about to try to solve their problems. And, you know, in a sense, we created a machine that doesn't have a trouble repeating the same process a whole bunch of times. And so we solved the problem using technology. Well, they solved it using calculus. What about this? Can you estimate that without a calculator based on your knowledge of the unit circle? Notice that angle's in radians.
0.
Sine of 1. Where are you if you're at an angle of 1 radian?
0.
No, you're thinking of you're mixing up kind of X and Y coordinates. Because this up here is 1.57 pi over 2. 1 would be like right about there somewhere. You agree with that? So in the unit circle, we cruise around that direction. Notice how much harder this is. Like you're probably a lot better at estimating the square root of 104 than you are at estimating when trig is involved. Or even worse, we'll do another problem in a second with natural log or cube root. But if I ask you to estimate natural log, I bet you're even worse at that. So I'm going in order of what you're best at to worst. And yet this method allows you to get a really good answer to these questions without having to work that hard. So I'm looking at this as thirds. Like if that's 0.5 radians, 1 radian, 1.5, that's about how I know where that is. And so I don't know, what does that look like to you? Since the unit circle, the y coordinate takes us up to a distance of 1, the y coordinate's 1. To me, that looks like, I don't know, what do you think, 0.8? I'm going to go with 0.8.
3.
I'm thinking it's 0.8. This is my educated guess. Based on my drawing.
Pi over 3 is pretty close to 1 too. We know that one.
Yes. Nice job. We're going to use that in just a second, Logan. So again, what's the process here? Well, like last time, we got to just kind of find some point that's close by. Now remember, if we consider the graph not y equals the sine of x, like last time it was, we want to know the square root of 104. And so we said, okay, well then let's consider the equation y equals the square root of x. Well, this time it's the sine of 1, but in order to get a shot at it, then we'll replace the 1 with an x and we'll say, let's consider sine of x. Now remember, the unit circle allowed me to guess this, but the graph of sine of x is not a circle. And as I said last time, well, why don't we go get a good graph of this instead of some ugly one like the one I just had a second ago. So if I say y equals, you know what sine looks like, but let's remind ourselves. So awesome. So there's our graph. Give ourselves a little room so it'll fit on there, nice and large so we can see it. So no different than before, but again, I don't know about you, but the like, is sine a circle or is it a sine wave? Like what's going on with that? Remember, the circle is what happens if you just watch what happens to the y coordinates as the y coordinates work their way from 0 up to 1, back to 0, down to -1. It just goes from 1 to -1, vacillating between. That's what creates the circle. But the actual graph looks like this. And so what we're saying is, hey, we're interested in 1. Well, isn't 1 right there? And so I want to know that y coordinate. Notice, since 1 is over here, that's the same look as it had a second ago, which is now that I actually have an accurate graph, 0.8, I'm actually even more encouraged to think 0.8 is the right answer to this. That does look like, wouldn't 0.75 be right in the center right there? So now I'm really thinking my guess was good. I'm actually happy with it now. Before I wasn't really all that sure. So we have the same problem we have that we had last time, which is that's the y coordinate of that is what I want to know. Isn't the y coordinate? So this is the point 1 sine of 1. Isn't that the coordinate of that point? So the y coordinate is what I'm after, but I don't know what the sine of 1 is. So the question is the same as last time, which was, I don't know what the square root of 104 is, but is there any number nearby that I know the answer to? And this is where what Logan said comes into play. He probably really didn't listen very carefully to what he said, but I want you to think about it mentally. Is there something nearby that we do know the sign of? Does it make sense we don't want to be over here somewhere? I don't want to be over here, because is that tangent line going to give me a good estimate? I'm not even in the same universe. Like I need to be close to that other point.
The sine of pi over 3, which is the square root of 3 over 2.
Yeah, both Logan and Justin pointed out or noticed that pi over 3, think about what pi over 3 is. If x is equal to pi over 3, well, isn't pi 3.14? So if that's true, we know the sine of pi over 3. Where is that point? Based on what I just wrote, is it below it or above it? Is it to the left of it, to the right of it?
Above it.
Yeah, notice it's 3.14 over 3. So that's more than 1. So we must be like here somewhere. And I'll purposely kind of draw it a little further away. Maybe right there. So again, like last time, what I'm after is, well, this tangent line. Yeah, I don't like that one. I'd like to kind of make it be a little worse on purpose if I could. Yeah, I like that. So if I can find the equation of that line, and you should be able to see I'm exaggerating. That point is actually a lot closer to the red point than what I drew. Since I can know everything about that green point, then I can find the equation of that line, and then I can use the line to cruise over to the x that I'm interested in. Just like last time I said, I have a line now, and then I cruised over to x is 104. Well, if I turn sine into a line, if I approximate sine by making a line, and as I said before, it's no different this time. If I get really close to that point right there, doesn't the blue curve and the green line look about the same? But would you also agree this is curvier than last time? I bet you my estimate isn't quite as good. But of course, your estimate also depends on how close you are. And I think 3.14 over 3 is really close to 1. So maybe it won't be such a terrible estimate. But the process is exactly the same. So I say, what do I know about that point? Well, I do know the sine of pi over 3. And I don't know about you, but I don't have that memorized. Like I have to either cheat and look it up on my unit circle, or I have to, let out a big sigh and go spend 20 minutes and build it for myself again. And I would ask you rhetorically, can you do that? Can you build that? Or are you utterly stuck without cheating on your calculator, or as I'm about to do, flipping to your note sheet that I sent you and just stealing it off the note sheet? If you can't build it for yourself, then you borrowed it. You don't own it. You got to give it back. It's like borrowing your neighbor's mower. Wish I had my own. You should take it upon yourself to go build that. Let's see, what's the sine of pi over 3? It's the y coordinate. It's the square root of 3 over 2. So that means I know the actual coordinates of the point. X is pi over 3. Y is the square root of 3 over 2. I know that. And I also need the slope, which is where calculus comes in. So what's the slope? Well, to get that, of course, I got to take the derivative of sine, which, as you remember, is cosine. And then I can evaluate that at the point that I do know, pi over 3. I can't evaluate it at 1 because I don't know that either, but I can evaluate it at the point that I do know. And I see on the chart that that's actually a half. So now I have everything I need. I have a point and I have a slope. So I like finding the equations of lines kind of the, I don't know, the old-fashioned way. I don't like to use a formula because I'm just going to forget that formula. I like to think, I know the slope goes there, and I know that x is pi over 3, and I know that y is supposed to be the square root of 3 over 2. So let's see, what does that imply? The square root of 3 over 2. I'd have pi over 6, but I'd have to subtract that to the other side. So isn't that b? So my tangent line, should be doing this in green. Maybe I'll switch. My tangent line is y equals 1/2 x, and then my b is, well, this kind of ugly expression.
Yeah, I guess you could make it 3 times square root of 3 minus pi over 6, but that's kind of whatever.
Yep, well said. In other words, I could find a common denominator and add those together, and so that's certainly an option. And of course, you know, again, I find myself thinking I'd rather just turn it into a decimal, like get my calculator out and turn it into a decimal. But again, that feels kind of funny because it's like, well, then get your calculator out and find the sine of 1. But like, again, what good is this? Yay, found the equation of the tangent line. What good is that?
Because it's going to give you a point close to what you were trying to find.
Yeah, the point is I can't plug 1 into the sine equation and get an answer because I don't know what the sine of 1 is. But I can plug 1 into a line. Like a line is multiplication and addition and subtraction. Like I can do that without a calculator. So now that I know this line, then I can proceed as we did before and say, fine, then what is y of 1? 1/2 times 1 plus all that gobbledygook. So I think I will make everything into common denominator. So y of 1 is this, which is a darn good approximation for the sine of 1. And based on the graph, is this high? Is my estimate there high or low? In this case, again, my green curve, my green line is above the blue. And so I actually know that this is high. This is a high estimate. Now, again, I think it's funny to say equals here. I don't think it makes a whole lot of sense to say equals here and act like you got sine of 1 exactly right. Of course, you know, that I find myself looking at that number going, well, that doesn't really help much. So I want to figure out what it is. 3 plus 3 square root 3 minus pi is 5 point something, all divided by 6. So this is approximately 0.842. And I know this is a bit high, right, from the graph.
Yeah, but it's still within a thousandth.
Yeah, so you busted out your calculator. I haven't done this yet, but the sine of 1 is actually, I'm in degree mode apparently.
Yeah, I did that too.
Well, that's good to know I'm not alone. So the calculator check says the sine of 1, this is what Justin was just alluding to, is 0.841. Wow. Again, not only did I get a good estimate, but I even knew it was a little high. That's amazing. I'm accurate by to 1/1000th. And, you know, what's this look like to an ancient person, you know, that doesn't have any way of getting the sine of 1?
That's pretty much right.
I mean, it's pretty darn accurate. I mean, this is really cool, isn't it? So again, it hangs on the fact that your graph isn't too curvy, and it's really important to choose a point nearby. Do you understand the magnitude of that statement? If you choose a point that's clear over here, you're not even going to be in the universe of the right answer. It's got to be nearby. You got to be able to find something nearby. And to that end, these problems will be a little bit canned. In other words, I didn't ask you for the sine of 2. I asked you for the sine of 1 because I thought of it ahead of time, and I thought there is something near 1 that you know. And I said, what's the square root of 104? I didn't say what's the square root of 187. I picked something that was really close to something that you know. The closer you happen to be to a point you know, the better your answer will be. And so these are both kind of canned examples. So, you know, 2, as an example off the top of my head, 2, you know, where's the sine of 2? Is there anything close to that? Well, I'd have to think about that a little bit. I don't know off the top of my head. I got to play around with it. What do I know that's nearby? Amazing. Here's another canned problem, but I'm going to let you try to think about this. This is even worse. If you are sharp, then you should be able to estimate, as I did, the sine of 1 is about 0.8. But notice I have no way of ever being more accurate than that. That wasn't a bad guess, but it's, remember, we just found out it's actually 0.84. And so my estimate wasn't that great, but at least I actually know what I'm talking about. I estimated something reasonable. But don't write this one down, because I'm going to modify it to make your life a little bit better now. But what if I asked you for like the natural log of 17? Can you estimate that? Can you even estimate it at all? My guess is lots of you probably can't. I know I graduated from college with a math degree, and I wouldn't even have known where to start because I didn't really understand what a logarithm was. I knew all the buttons to push because I lived in the world of calculators, and I didn't need to estimate it because I got a calculator in front of me. Why would I estimate it? What a dumb waste of time. But I didn't really know what logarithm is. So my guess is you're not very good at estimating this. Now, you should be able to do a little better with this, though. This is more of a canned question. Why, somebody enlighten us, why do you kind of know the answer to that one?
This isn't natural log like 2 point something, or is that just E?
That's E. Natural log E is 2, and it does connect to E. You're right about that. E, remember, is approximately 2.718. That doesn't look like a 2. Start over.
It looks like 1.
Yeah, it looked like a 1. And you actually know the natural log of E. Well, you might remember it. The natural log of E is what?
1.
It's 1. Therefore, the natural log of 3, then, I would guess, is, well, a little over 1. Does that make sense? Just to close the loop a little bit, I made up 17 randomly, and I do know how to estimate this now. Remember, logarithm answers the question, since this is base E, it answers the question, E to what power is 17? And since E is about 3, then I could say 3 to what power is 17? Well, 3 squared is 9, and 3 cubed is 27. 3 squared is 9, and 3 cubed is 27. So I'm guessing if I kind of back all the way up, then this question mark here is between 3 and 2. I can estimate that now. But again, I'm not kidding. When I graduated from college math degree, couldn't do that. Didn't really understand what logarithm was. Logarithm is answering an exponential equation, just like square root is answering a squared equation. So if I said, what's the square root of 17? You would think in your head, that's some number that when squared is 17. In other words, you switched it from a square root or a radical function. You switched it to square, which you do understand. And you say, oh yeah, something squared is 17. I understand squared. And then you make an estimate. Well, it's the same thing I did here. I switched out of logarithm because you can't make any sense of a logarithm, just like you can't make any sense of square root unless you think of it as its opposite. Anyway, that's a free side note about algebra that you should know, but likely don't. So, armed with the fact that, if you will, E is nearby, or I'll just say it's near 3, and you know the natural log of E is 1, let me give you a second to just see if you can set this up yourself. I've shown you a couple examples. If I don't know if you can see that well enough to read it or if it's too small, but if I ramp that back so you can see the previous example, take a stab at it. Again, just like square root and sine, logarithm is a button we rely on our calculator, but the ancients did not have that luxury. So this was really cool for them. There's the graph if it helps you. You don't need the graph, it just helps you to visualize a little bit. The cool thing about your era is you actually have a calculator, so you can check it, like whatever answer you get. Notice thanks to the graph, you could estimate it. I can see it's above 1, and this is 1.5. So can I divide that into 5 marks? 2. No, that's more like quarters. Yeah, that now looks to me like 1.1. No. Yeah, 1.1. So I can't do that without a graph. But we're at 2.718. 2.75 would be right there. Actually, I even drew that a hair to the left. I think I'll go with that. So we know that E is right there. And notice, hey, look, it's at 1. The y coordinate's 1. Of course it is. The natural log of E is 1. So I know that ordered pair. Now, based on the graph, would you say this is going to be a good estimate or a bad estimate?
Good.
It's going to be extremely good. I don't know about you, but if I zoom in like that and I say, what is that curve right there? It actually looks like a line. So we're close to it, and the blue graph is a line. Does it make sense to you if the blue graph looked like this? Then we'd have a pretty lousy answer. So again, I'm making up kind of canned problems, that are going to come out nice. They don't always come out nice. Just for visual effect, again, I'm going to draw my tangent line. Let's see, am I happy with this tangent line? So yeah, that's going to be just barely above it. Again, this is also going to give me an overestimate. Every example I've done so far has been an overestimate. This is going to give me an excellent overestimate. I can tell that right now. I'm not a believer in steps. I'm a believer in thinking. But in a sense, the first thing you got to do is find some point nearby that you actually do know the answer to. We found the square root of 100 was nearby. We know that. We found the sine of pi over 3 was nearby, and we know that. We found the natural log of E, which is nearby, and we know that. So we found a point. Now we've got to go get the slope, which of course I take the derivative. I consider the function the natural log of x, not the natural log of 3, which was my original problem, but the natural log of x. And I say, okay, let's go get its derivative. Well, that's an easy derivative. Derivative of natural log of junk is 1 over the junk. Fortunately, it's just x. So you would say the derivative of natural log of junk is 1 over junk times the derivative of the junk, but remember the derivative of x is 1. Again, I would ask you rhetorically, could you make that for yourself? Do you remember how we did that? I mean, the answer to that should be no. Like, I doubt you remember it. Maybe you do if you got a better memory than me. But like, go back and try to get that again. Try to go grab that again. Like, can I make that for myself? Can I show that to somebody? Can I explain why that is? If I forget it and don't have my notes, could I build it for myself? I love the concept of, like, I love watching survival shows, and it's like, oh dang, I don't have matches, and the fact that they can take a shoelace off and know exactly what kind of woods are nearby, and soft and hard woods, and they can make a bow, and it's like, well, I can make my own fire. I actually don't need a match. I mean, that's just kind of cool. I love that sense of independence. I feel the same thing here in a much nerdier way. Okay, I found its derivative, which of course I'm going to use to, based on the picture, if you understand what it is you're doing, I need the slope at the point E1. I need the slope there because I'm trying to find the equation of the green tangent line. And so I'm going to get it by plugging E in. That's interesting. So
yeah, I got 1 over E for the slope.
Yeah. So there's our slope. So we have a slope, we have a point, we have everything we need then to go find the equation of the tangent line. It's time to go green, since that's what the color of my tangent line was. Equation of the tangent line.
Yeah, I ended up with y equals 3.1 something something.
Yeah, and there's nothing wrong with getting your calculator out and switching E to a decimal, figuring out what that number is as a decimal. That's totally fine. But I'm just going to do it sort of mechanically first. And so I know the equation looks like that. I know the point X is E and Y is 1 is supposed to work. Hey, that's interesting because you end up with E divided by E, which is 1. So you have 1 plus what is 1? Well, B is nothing. That's kind of cool. So that means the equation of your tangent line is just 1 over E times X.
Yeah, I messed up there. I ended up with B equals 2.
Incidentally, stare at the graph. If you look at my graph, could B be 2? I'm always encouraging you to think, and you watch me make dumb mistakes every day, but that's why I always kind of stop and think. Like,
no,
the y-intercept, and it's like clearly that green line is aiming down. To me, it looks like about there somewhere. So I'd expect to get something a little bigger than 0. So the fact that I got 0 just means that I probably didn't draw my tangent line very tangent. I mean, it was a guess, right? So, but at least it's reasonable that I got 0. Again, I think you have to slow down and think to understand this. If you just follow steps, you're going to get all kind of jarbled up here. But what do I do now? Well, now I have an approximation of the blue curve, except the green curve is easy to work with algebraically. So although I can't plug 3 into the natural log of X, that's what the problem was in the first place, I can plug 3 into my green equation totally easy. So my last move is just to say, cool, well then put 3 in there, since that's what you're after in the first place. And notice I get 3 over E. And if for some reason somebody wanted it exactly right, then great. But in my calculator, if I take 3 divided by E, I get approximately 1.104. So I can say then that the natural log of 3 is darn close to 1.104. And even better, this is an over, because of the graph, this is an overestimate. So when I bust out my calculator to kind of check my work, and I say check What is the natural log of 3? Since I have a magic machine, again, I doubt any of you know how your calculator is doing this. How does your calculator know what the natural log of 3? Since ultimately what the natural log of 3 is e to what power is 3? Like, how in the world is it getting that? Lovely math waiting for you down the road if you choose to stay the course. I got 1.099. Sure enough,
Yeah,
it's really close. It's 5/1000ths off. And the purple indeed was an overestimate. That is amazing that that worked so well.
I would have had it if I didn't think that 1 minus 1 was 2.
Yep, it's the old 1 minus 1 is 2 ploy. A lot of people have ran that program. So as I said, what I consider to be the value of this is more just a thought exercise, because it's irrelevant in the culture in which we live. So the questions in your assignment are, like this, but some of them are modifications. They're around this idea. If you understand this idea deeply, and you see that I just did 3 examples of the same thing, you understand that I'm just finding a line tangent to the curve at some point near the point you're after, then you'll be able to make the connection to homework assignments. I don't think I'll do another example, but we could do the cube root of I'm going to erase this, but the cube root of 65. Why is that a good problem to do? Because again, you're probably really bad at cube roots, right? Like, what's a cube root? Oh man, I'm terrible at that. Or if I made it a 5th root, you'd be terrible at that. Why did I pick 65 though? I could have put any number in there I wanted. Why did I pick 65?
Cube root of 64 is 4.
Cube root of 64, super close to 65, and it's exactly 4. And so this estimate would be fantastic. But as I said, if I make this up randomly, and I said, I don't know, like the 5th root of 193. I don't know about you. I'm terrible at that. Like, I'm really going to have to think, because I'm going to have to think what number times itself 5 times is in the vicinity of 193, right? And 193 might not be a very nice number. But the cool thing is you can estimate a 5th root. You can estimate anything you want. All of these, well, these are all functions. Natural log is a function. Square root or cube root are functions. Sine is a function. And so those are equations. And because we can take derivatives, then we can get answers that are nearby. That's just kind of a cool concept. But I'll be asking a question on a test, well, like one of these. As I said, just kind of going out the door, because I just want to say this again really quickly. In a later section, there's something called Newton's method. I can't remember what section it is, but it's coming up. It'll be like first of next week, right before the test. But Newton's method uses that idea. If you have a curve that kind of hits the graph right here, and you're trying to figure out what the coordinates of that is. So then you say, hey, I know the answer to it over here. So then if you made a tangent line, so this is kind of guess number 1, that's your guess. If you make that tangent line and you see where that tangent line hits the curve, that represents guess number 2. And it's now closer to the one before, but notice it's not great because this is a very curvy curve. But then if you proceed up to where that hits the curve, and then you draw another tangent line, notice now guess number 3 is really close. And if I go up to where I hit the curve again and do this again, now it's kind of like within 3 iterations of this, you're right on it. I mean, that's kind of the idea. And so this is making use of the exact same thing. You got this weird, crazy curve that you don't understand. Well, approximate it with a line. Lines are good approximations as long as you're close, as long as you're near the curve, then that's going to be reasonable. So we'll play with that idea some more later on. Okay, let's get out of here early. And if you want to talk homework, we'll stay after and do that, but I'll post this discussion and my notes after class. And I will see you after a glorious weekend. I hope you have a good one.
4.7 says it's
Yeah.
due next Sunday.
4.7 is due.
On
Next
Sunday, yeah.
Sunday.
Something is wrong with due dates. Okay, I'll fix that. Let's see. Oh yeah, 4.6. 4.7 is something I could have talked about today. Low Patal. I forgot about Low Patal. I'm either going to unassign that or change the due date. I don't know which. So I'll fix that.
Well, I have to get to my next class, but I likely will bother you